The process in a steel plant involves several stages, each critical for transforming raw materials into finished steel products. The key steps in steel production are as follows. 1. Iron-making blast furnace or direct reduction. Blast furnace, the most common method for making iron, where raw materials, iron or coke, and limestone, are heated in a blast furnace to produce molten iron, called pig iron. Direct reduction. In this process, iron ore is reduced using a gas, typically hydrogen or carbon monoxide, to produce direct reduced iron, DRI, which can then be further processed into steel. 2. Steelmaking basic oxygen furnace or electric arc furnace. Basic oxygen furnace B. The molten pig iron from the blast furnace is refined by blowing oxygen through it, which reduces the carbon content and other impurities, turning it into steel. Electric arc furnace EAF. Instead of using pig iron, this method primarily uses scrap metal as raw material. An electric arc melts the scrap metal, and then impurities are removed to produce steel. 3. Secondary steelmaking. This stage involves further refining the steel to meet specific quality requirements. Processes like ladle refining, alloying, adding elements like chromium, nickel or molybdenum, and adjusting the temperature are used to achieve the desired chemical composition. This is usually done through continuous casting, where the molten steel is poured into molds and cooled. 5. Hot rolling. The cast slabs or billets are heated and passed through rollers to reduce thickness and shape the steel into desired forms, such as plates, coils, or beams. 6. Cold rolling optional. For certain products, steel can be further processed by cooling it down and passing it through rollers again to achieve a smooth, shiny surface and precise dimensions. Cold-rolled steel is used for applications that require a high level of surface finish and precision. 7. Finishing processes. Steel products are often finished with treatments to enhance their properties, such as pickling, removing scale or rust from the surface, galvanizing coating steel with a layer of zinc to prevent corrosion, annealing, heating the steel and then cooling it slowly to relieve stresses and improve ductility, heat treatment, adjusting the temperature to harden or soften steel for specific applications. 8. Quality control. Throughout the entire process, quality control measures are essential. Tests for tensile strength, hardness, surface finish, and chemical composition are conducted to ensure the final product meets specifications. Certainly. Here's a more detailed breakdown of the processes involved in a steel plant, including some additional steps, technologies, and considerations. 1. Iron making, blast furnace versus direct reduction. Blast furnace. The blast furnace process is the most common method of producing molten iron. Iron ore, mainly Fa2O3 or Fa3O4, is combined with coke and limestone. Coke acts as both a fuel and a reducing agent, and limestone helps remove impurities. The blast furnace uses high-temperature air blasts to melt the iron ore, producing molten pig iron and slag, a byproduct of impurities. The reaction in the blast furnace can be simplified as 2, 3, 3, gives 2, 3, 2, free, 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 plus 3C, gives 2 free, plus 3C, O2. This process eliminates the need for a blast furnace, and instead, uses natural gas or coal to reduce iron ore directly to iron without the use of coke. This process produces direct reduced iron DRI, which can be further processed into steel. Pros of blast furnace. Better suited for large-scale operations and continuous production. Steelmaking. Basic oxygen furnace versus electric arc furnace. Basic oxygen furnace, BOF. The BOF is the traditional method used in integrated steel plants where steel is made from pig iron. In this process, molten pig iron is transferred into a large vessel called a converter, and oxygen is blown through the molten iron. The oxygen oxidizes carbon and other impurities, reducing their concentration. The reaction results in the formation of steel. The typical reaction in BOF is 2, gives which reacts further, FeO2, gives Fe which reacts further. The BOF can also use small amounts of scrap steel to help control the chemical composition of the steel. Electric arc furnace, EFN. In EAF, scrap steel, often 100% recycled steel, is melted using electricity. An electric arc is struck between large electrodes and the scrap steel. The process is highly flexible and can be adjusted for smaller batches, making it ideal for producing high-quality steels for specialized applications. Secondary steelmaking, refining and alloying. After primary steelmaking, steel may require further refinement. This stage aims to fine-tune the chemical composition, remove excess impurities, and add specific alloying elements such as chromium, nickel, or manganese, to achieve the desired steel properties. Ladle refining. This process takes place in a ladle, a large refractory-lined container, where various adjustments are made, such as temperature control, deoxidation, removal of excess oxygen, and alloying. Gas purging with inert gases like argon helps homogenize the molten steel. Vacuum degassing. This process is used to further reduce the levels of dissolved gases like hydrogen and nitrogen, which can negatively affect steel properties. By applying a vacuum to the molten steel, these gases are removed. For casting, continuous and ingot casting. After refining, molten steel is cast into various shapes. Continuous casting offers better product consistency and higher yields. Ingot casting. In older methods, molten steel is poured into large molds, known as ingots, and then reheated and processed further. This method is less efficient compared to continuous casting, as it results in more waste. 5. Hot rolling. Shaping the steel. Hot rolling is a process where cast slabs or billets are reheated to a high temperature, usually above 1000 degrees Celsius, and then passed through a series of rollers to reduce thickness and shape the steel into final forms like sheets, plates, coils, and structural shapes, angles, beams, etc. Hot rolling not only shapes the steel but also refines its grain structure, improving its mechanical properties. 6. Cold rolling. Finishing for precision. After hot rolling, some steel products undergo cold rolling, a process where the material is further reduced in thickness at room temperature. Cold rolling improves surface finish, dimensional accuracy, and mechanical properties such as tensile strength and hardness. Types of cold rolling products. Cold rolled coils. These are used for products like appliances, automotive parts, and construction materials. Annealed steel. This is steel that has been heat-treated after cold rolling to soften it and reduce internal stresses. 7. Some of the common finishing processes include pickling, a process to remove oxide scale rust from steel surfaces using an acid bath, typically hydrochloric acid. Galvanizing. Steel is coated with zinc to protect it from corrosion. This is done by dipping steel into molten zinc or through electrogalvanization. Heat treatment. Steel is heated and cooled in a controlled manner to achieve desired properties such as hardness or toughness. Examples include quenching, rapid cooling typically in water or oil, to harden the steel. Tempering, reheating quenched steel to reduce brittleness and improve toughness. Annealing, slowly cooling steel to relieve internal stresses and increase ductility. Coating. Some products, such as automotive steel, may receive coatings like paint, anti-corrosion treatments, or even plastic coatings. 8. Carbon capture and storage, CCS. Some steel plants are investing in carbon capture technologies to reduce CO2 emissions. Recycling. Using recycled scrap steel in EAFs is one of the most effective ways to reduce the carbon footprint of steel production. Approximately 90% of the raw material used in EAFs comes from scrap steel, significantly reducing the need for mining iron ore. 9. Quality control. To ensure that steel meets the required specifications, quality control is conducted throughout the production process. Chemical non-destructive testing (NDT) techniques like ultrasonic testing, magnetic particle inspection, and eddy current testing help detect surface or internal defects in steel products without damaging them. 10. Distribution. After finishing, the steel is ready for delivery to customers. Steel is often shipped in coils, sheets, or large structural shapes, and it may be processed into final products in industries like automotive, construction, machinery, or appliances. Certainly, let's dive deeper into some of the aspects of steel production that are essential for improving efficiency, sustainability, and the quality of the steel produced. 1. Advanced steelmaking technologies. The steel industry continues to innovate with advanced technologies aimed at improving quality, efficiency, and reducing environmental impacts. Some of these include hybrid steelmaking. This process combines the benefits of both blast furnace and electric arc furnace methods. In hybrid steelmaking, the molten iron from a blast furnace is used as a raw material for the electric arc furnace, which helps reduce energy consumption and carbon emissions. Hydrogen-based steelmaking, one of the most promising innovations in steelmaking is the use of hydrogen instead of coke for reducing iron ore. Hydrogen reacts with iron ore to produce iron and water vapor, H2O, instead of carbon dioxide, CO2. This method has the potential to significantly reduce the carbon footprint of steel production, but it is still in the pilot phase in most countries. Oxygen steelmaking, pure oxygen. Some plants are switching from air to pure oxygen in the steelmaking process. This change improves the efficiency of the process by increasing the reaction temperature, allowing for better impurity removal and faster processing times. Top gas, recycling blast furnace. In this variation of the traditional blast furnace, the waste gases produced during the reduction process are recirculated and used to preheat the incoming iron or an air. This helps recover energy that would otherwise be wasted and reduces the amount of fuel needed. 2. Energy efficiency and environmental impact. Steel production is an energy-intensive process. Reducing energy consumption and minimizing environmental impact are key goals for the industry. Energy efficiency, heat recovery systems. Modern steel plants use advanced heat recovery systems to capture and reuse excess heat from the production process. This not only saves energy but also reduces fuel consumption and emissions. Improved furnace technology. New furnace designs with better insulation, optimized burners and advanced temperature control can increase energy efficiency during both ironmaking and steelmaking. Carbon capture, utilization, and storage CCUS. Carbon capture technologies are being tested to capture CO2 emissions from steel plants and store them underground or use them in other industrial processes, such as producing chemicals, synthetic fuels, or building materials. Renewable energy integration. Many modern steel plants are working on integrating renewable energy sources, such as solar or wind, into their production processes. The electricity generated from renewables can be used in electric arc furnaces, which already have a relatively lower carbon footprint compared to traditional blast furnaces. Use of biomass and biofuels in some plants. Alternative fuels like biomass, such as wood chips or waste from agricultural processes, are being tested to replace coke or coal in the reduction of iron ore. This reduces the carbon intensity of steelmaking and moves the industry closer to a circular economy. 3. Automation and digitalization. The steel industry is increasingly adopting Industry 4.0 technologies to improve the efficiency, flexibility, and safety of steel production. Automation. Steel plants are incorporating automated systems for better control of production processes. Robotics and automated systems are being used for tasks like material handling, quality control, and even complex operations such as casting, rolling, and finishing. Real-time monitoring and control systems. Sensors and artificial intelligence AI are being used for real-time data collection and process optimization. These systems allow operators to adjust parameters on the fly, improving yields, reducing defects, and minimizing energy consumption. Artificial intelligence and machine learning, AI and machine learning algorithms are being implemented to predict and optimize production schedules, detect process inefficiencies, and identify potential equipment failures before they happen. Digital twin technology. In some advanced steel plants, digital twins are being created. A digital twin is a virtual replica of the physical production process. It uses real-time data to simulate how the process behaves, allowing engineers to test different scenarios and improve operations without making physical changes to the plant. For recycling and scrap steel. Scrap steel recycling. The steel industry is one of the most efficient industries when it comes to recycling. Steel is 100% recyclable without losing quality, making it a perfect candidate for circular economies. Steel scrap is often recycled in electric arc furnaces, which melt down scrap steel to produce new products. Steel scrap grades. The quality of the scrap used plays a crucial role in the properties of the finished steel. Steel scrap can vary in purity, and sorting scrap by grade is an important step in maintaining steel quality. With the development of better sorting technologies and stricter recycling regulations, scrap steel can be processed more efficiently and with fewer impurities. Urban mining. In addition to traditional scrap recovery from manufacturing processes, urban mining refers to the recovery of scrap steel from discarded products such as old cars, appliances, and construction materials. This process is increasingly being recognized as a valuable source of raw material, particularly as the demand for steel rises. 5. Product diversification. The steel industry is producing more specialized products to meet the diverse needs of different sectors. High-strength steel. With advancements in alloying and heat treatment technologies, steel can now be made with higher tensile strength, while maintaining good formability. This type of steel is crucial in industries like aerospace, automotive, and construction, where high strength-to-weight ratios are needed. Stainless steel. Stainless steel, which contains chromium and other alloying elements like nickel, is used for applications that require corrosion resistance, such as in kitchen appliances, medical instruments, and architecture. Stainless steel production is growing, particularly as industries and consumers demand materials that are durable and can withstand harsh environments. Advanced high-strength steels AHSS. AHSS is increasingly used in the automotive industry to reduce vehicle weight while maintaining strength and safety standards. These steels often include alloys such as manganese, boron, and nickel, and are designed to absorb more impact energy in case of a collision. Electro-galvanized steel. Steel that has been coated with a thin layer of zinc via it is often used in automotive and appliance manufacturing for improved corrosion resistance. 6. Challenges and future directions. Decarbonization. The primary challenge for the steel industry moving forward is decarbonizing its operations. The steel sector is responsible for about 7 to 9% of global CO2 emissions, largely from the blast furnace method. Transitioning to hydrogen-based production and improving the efficiency of electric arc furnaces are seen as critical steps toward reducing carbon emissions. Global supply chain and trade dynamics. The global steel market is highly dynamic, with shifts in production volumes and trade regulations influencing global prices. Trade wars, tariffs, and competition from emerging economies can impact steel plant operations worldwide. Technological adoption and investment. The shift towards new technologies, such as hydrogen-based steelmaking or carbon capture, requires substantial investment. Smaller steel plants might find it challenging to adopt such technologies without external financial support or partnerships with larger, more capital-intensive companies. Circular economy and sustainability. As part of the broader push for sustainability, the steel industry will need to continue pushing for a circular economy model, finding ways to repurpose materials throughout the supply chain. 7. Conclusion. The steel industry is undergoing significant changes driven by technological advancements, environmental concerns, and changing market demands, with the growing emphasis on reducing carbon footprints, improving energy efficiency, and meeting specialized product requirements. The future of steel production looks to be more sustainable, automated, and technologically advanced. However, challenges such as decarbonization, technological investments, and global competition remain key considerations for steel producers going forward. 1. Emerging steelmaking technologies. Molten oxide electrolysis. One of the cutting-edge technologies being explored for low-carbon steel production is molten oxide electrolysis. This process involves applying electricity to molten iron ore, which eliminates the need for coke as a reducing agent and produces oxygen instead of carbon dioxide. This process shows promise as it could potentially replace both the blast furnace and electric arc furnace, making it one of the cleanest ways to produce steel in the future. Hydrogen-based DRI. The use of hydrogen to replace carbon and direct reduction of iron dry is a highly researched area. Hydrogen-based direct reduction is seen as the future for green steel, because hydrogen, when used as a reducing agent, only produces water vapor as a byproduct, making the process nearly carbon-free. Sweden's hybrid project and other global initiatives are already piloting hydrogen-based ironmaking technologies. Electrochemical steelmaking. Researchers are investigating electrochemical processes that use electricity to reduce iron ore into steel directly. These techniques focus on the electrochemical reduction of iron ore without the need for high temperatures or a furnace. This could drastically reduce both energy consumption and carbon emissions associated with traditional methods. 2. Advanced alloys and specialized steels. Dual-phase steels, DP steels. Dual-phase steels are used primarily in the automotive industry, offering a combination of high strength and good ductility. These steels consist of two phases, a soft ferrite phase and a hard martensite phase. The combination allows these steels to absorb energy in a crash while still being lightweight. The steel's properties can be tailored by controlling the heat treatment process. Third-generation advanced high-strength steels 3GAHS. Third-generation AHSS is designed for use in industries like automotive manufacturing, where lightweight but strong materials are required. These steels are made by combining microalloying elements and advanced cooling methods to produce materials that maintain their strength while being easier to shape. They often include complex microstructures that optimize the balance between strength, formability, and toughness. Titanium steels. Titanium steels are designed to be highly resistant to corrosion and high temperatures. They are used in highly specialized applications such as aerospace, military, and chemical industries. The challenge in manufacturing these steels is maintaining their high strength, while preventing titanium from negatively reacting with other alloying elements. Tool steels and high-speed steels. These steels are formulated for use in manufacturing tools that need to withstand high stress and wear. They often contain high levels of carbon, chromium, and tungsten, which provide hardness and heat resistance. Advanced tool steels have been used in precision industries like cutting tools, dies, and molds, where toughness and durability are key. 3. Sustainability and environmental impact. Moving toward green steel. Circular economy and byproduct utilization. A circular economy approach involves the continual reuse of steel products, such as scrap metal, through recycling and electric arc furnaces, EAF. In addition, byproducts like slag from blast furnaces are being recycled into other industries. For example, blast furnace slag can be used in the production of cement, road construction, and even as a fertilizer in agriculture. Zero carbon steel. Steel producers are working toward achieving zero carbon steel production. To this end, companies are adopting various methods, including carbon capture and storage, CCS technologies to capture CO2 emissions from the blast furnace, renewable energy, wind, solar, hydro, 2-power electric arc furnaces, hydrogen-based steel production that eliminates carbon emissions entirely. Companies like SSAB, Tata Steel, and ArcelorMittal have been investing in these methods to transition the steel industry toward carbon-neutral practices by 2050 or sooner. Carbon-free steel by 2030. A few countries, especially in Europe, have set ambitious goals to make steel production carbon-free or significantly reduce emissions by 2030. The adoption of hydrogen in the steelmaking process, in particular, is considered one of the most promising pathways to achieving this goal. By leveraging hydrogen as a clean fuel and reducing agent, the steel sector could significantly reduce its environmental impact. For innovative steel products for new industries. Smart steel and IoT integration. Smart steel is steel embedded with sensors and other technological innovations. These sensors are designed to monitor things like temperature, strain, and corrosion in industries like automotive and construction. Smart steel can be used for structural health monitoring, providing early warnings about potential failure points or stress on a structure. In automotive manufacturing, smart steel could also assist in the development of autonomous vehicles by offering smart, flexible materials that adjust to dynamic conditions. Steel for 3D printing. Steel is increasingly being used in 3D printing, where additive manufacturing processes build up layers of steel powder to create complex This technology is particularly useful in industries like aerospace, defense, and medical devices, where highly customized parts are needed. Companies are developing specialized steel alloys for 3D printing that retain the material's strength and integrity during the printing process. 5. Digital transformation in steel production. Big data analytics. Steel plants are now integrating big data analytics into their operations. Sensors installed throughout the production process gather vast amounts of data on temperature, chemical composition, mechanical properties, and more. This data is used to create predictive models that can help optimize the production process, minimize defects, and reduce energy consumption. Predictive maintenance, driven by machine learning algorithms, can also identify when equipment is likely to fail before it happens, minimizing downtime and reducing repair costs. Blockchain for supply chain transparency. The steel industry has been exploring the use of blockchain to track steel products from their source to end user, ensuring transparency and traceability in the supply chain. This technology provides the ability to trace the origin of steel products, ensuring that they meet sustainability and ethical standards. For example, blockchain can help verify the source of scrap metal and ensure that it's being recycled appropriately, contributing to the circular economy. 6. Steel production and the future of construction. High-performance steel for construction. Steel remains a dominant material in construction due to its strength, durability, and recyclability. New types of high-performance steel, including weathering steel which forms a stable, rust-like appearance when exposed to weather, are now being used in bridges, high-rise buildings, and other infrastructure projects. Lightweight steels are also emerging, which reduce material usage and transportation costs in construction. 3D printed steel for construction. The concept of using 3D printing for building construction has been gaining traction, particularly in creating complex shapes and structures that are impossible to produce with traditional construction methods. Researchers and companies are exploring 3D printed steel for creating custom building components, and even entire structures, with faster construction times and reduced labor costs. This could revolutionize the construction of buildings, bridges, and even infrastructure in remote areas. 7. Challenges facing the steel industry. Cost of transitioning to green steel. One of the biggest challenges the steel industry faces in transitioning to greener, more sustainable practices is the high cost of developing and deploying new technologies, such as hydrogen-based steelmaking or carbon capture systems. These transitions require significant upfront investment and may lead to higher production costs. Governments and industry leaders will need to collaborate to ensure that incentives and support are provided to facilitate this transition. Global competition and trade policies. Steel production is highly influenced by global supply chains and trade policies. Countries with abundant natural resources, such as China and India, continue to dominate the steel market, which puts pressure on steel manufacturers in other regions. Trade policies, tariffs, and subsidies often affect the global steel market, making it difficult for companies to compete on a level playing field. Automation and labor concerns. The increasing automation of steel production, while improving efficiency and safety, also raises concerns about job displacement. Automation in areas like rolling mills, casting, and finishing lines may reduce the need for manual labor, and the industry must find ways to reskill workers and manage labor transitions. 1. Steelmaking by advanced methods. CoreX process. The CoreX process is an innovative alternative to traditional blast furnaces for producing molten iron. It is a gas-based reduction process where iron ore is reduced to iron directly in a shaft furnace. CoreX technology is considered more energy efficient and environmentally friendly than blast furnace methods because it produces fewer emissions and can utilize a broader range of raw materials, including non-coke and coal, and even alternative biomass fuels. This process helps reduce reliance on coke and could play a significant role in reducing the carbon footprint of steelmaking. Finex process. Another alternative to the blast furnace method is the Finex process, which is similar to CoreX in its use of non-coke and coal for reducing iron ore. The advantage of Finex is its ability to directly convert iron ore into molten iron without the need for coke production, which significantly lowers both cost and environmental impact. It's also more flexible in terms of the types of coal used, which can be a great advantage in regions with limited coking coal resources. Electrosteelmaking. Electrosteelmaking is an emerging technique in which electricity, often generated from renewable sources, is used to reduce iron ore into steel. This process could bypass many of the emissions associated with traditional steel production methods. Electrosteelmaking has potential applications in the development of low-carbon steel, aligning with broader industry decarbonization goals. Plasma arc steelmaking. Plasma arc steelmaking is another advanced method where an electric arc created by plasma melts the metal. This method has higher efficiency compared to conventional electric arc furnaces (EAFs), and it can process scrap metal and certain iron ore products directly. The high temperatures in the plasma arc make it ideal for melting and refining various metals, including specialty alloys, with lower energy usage.